First thing, any questions about the syllabus? No questions? Okay, forgot to point out a couple of things in the syllabus. Maybe I did, but on the back of the second page is our daily outline. I did say, yeah, because we're already behind. What I did not point out is over on the right, this is your lab, what you're going to be doing each week in lab. So there's two, each of you have 2 labs a week, so that's divided in half. First lab of the week, check in, and then have IR lecture. That's what we did yesterday and what we will do today for the other group. And then on Wednesday and Thursday will be solubility testing. Dr. Idell will tell you about that in the lab yesterday, hopefully. So that's your lab outline. Daily. There was a modification need to be made because Memorial Day we're off. Dr. Idell told you about that. Everybody got the workbook? I mentioned periodic table yesterday. Last page in the workbook is periodic table, you know? Okay, where are we at? Green sheet, functional groups, hybridization. We're doing methane. We also have the white handouts, physical properties. Where's the other handouts? Just saw it. Oh. There you go. Another one, functional groups. The US warm-up. Any questions from these warm-ups? Functional groups, we went over those. DUS, we went over that. Determining bonds from formula, that's really miscellaneous. You can use that if you want, if it's helpful. Exceptions to the octet rule, that's miscellaneous. Information just to read. On the back though, these are some new drawings for me. I just tried to draw these out. Hybrids, what do the hybrids look like? We're going to refer to these. As I mentioned, SP3, because it has 75% P, so there's 3 P's that went into the blender. Looks more like a P. Main thing there is that it's longer, because the p orbital, if we draw it this way, it's longer. This end gets canceled out because when it mixed with the S, it got destructive overlap. So that's called the back lobe, and usually that's not drawn when we start drawing them all together around the atom. More S character. What's that, 25% S? 33% S. More like an S, so it's getting more rounded and also shorter. Okay? Now it's 50% S, getting closer to an S, and so it's more rounded. Now these aren't absolute depictions, this is relative, meaning that that one is shorter and rounder than this. Main thing is shorter. And so if you make bonds with something like this, it's going to be a longer bond. That's going to give you a shorter bond. Okay? Then we'll refer to this table. Really, when we sum it up, we'll look at this table. Okay, we'll look at the methane. By the way, you got to have a textbook. I mean, you've got to. The goal is to do well in the course. I would recommend having a textbook and working problems in the textbook, reading the textbook. I brought my textbook from when I was an undergraduate student. It's kind of falling apart now. Used to keep it under my bed. Kind of retired it, but 67 bucks, brand new. Then they'll get you about $250 more. Okay, get this fired up. SP3, look at methane. Try to draw a hybrid. So let's get back to where we were. We showed the ground state, and then we ended up with, after we hybridized, we ended up with a, how many hybrids? We're doing sp3 here. So we mixed an S and 3 Ps. If you put 4 atomic orbitals in the blender, how many hybrids are you going to get out? 4. However many you put in, you get that many out. We put all 4 in, all 4, S and 3 Ps. We blended it up, and we ended up with 4 sp3s. All have the same energy. We can put 4 valence carbon electrons, and then we can make 4 bonds to anything. 4 bonds to H's, 4 bonds to bromine, and we have 4 equivalent bonds. We can draw methane sort of like this, but this doesn't show the true bond angle or arrangement of the bonds. How are they really arranged? Okay, your hybrids set your geometry. We have how many hybrids? 4. 4 hybrid orbitals are going to be spread out best how? Tetrahedral. Okay, this is just nature. The electrons repel each other to a certain degree. They want to be spread out as much as possible. And the best way to spread them out is tetrahedral. For example, if I brought in 4 balloons and tied them all together at the tie point, guess how those 4 balloons would spread out? Tetrahedral. There's nothing magical about it. That's just nature. Okay? Well, what is tetrahedral? If we have this carbon, let's see if we can draw them out here. We have 4 hybrids around the carbon. I'll try to do this the same way so I don't have to think about it. I'm going to have to look at my notes. Let's put 4 orbitals, those 4 hybrids around here. What do they look like? Well, we tried to draw that. Let's draw maybe one up like this. Okay? And there's a little back lobe there. Remember the back lobe? There's one. Really, it's easier for me. I like to do things on the board real time because I'm showing you how I'm thinking. Okay? You can think too. It's easier for me to draw the orbitals, unless I just want to pull out something that's already canned and just repeat it. It's easier for me if I just draw in sort of tetrahedral as a line. What is tetrahedral? 2 in the plane, 1 forward, 1 back, with bond angles of what? 109.5. 109.5, okay? Those are the plane. 1 forward. Forward's going to be a bold, okay? It's like it's coming out towards you. And then 1 going away. Dashed, and as it goes away, it's tailing off, getting smaller. Now, all these bond angles are 109.5. And usually I don't have to bring my models until day 3 and 4, but today is day 3 and 4, right? It was a double lecture. Okay? So actually I did not bring. Okay. This is tetrahedral. 2 in the plane, 1 forward, 1 back. Now I can draw these orbitals here. This is really going to be an orbital. Okay? In the back lobe. But then you have an orbital like this in the back lobe. These are the 4 hybrids. And then you have an orbital like this in the back lobe. And then you have an orbital like this in the back lobe. And so there are your 4 hybrids around that carbon in a tetrahedral arrangement. Now guess what? Usually when you start drawing this, people don't draw the back lobe. Alright? But they're there. And again, Later on, we'll actually mention the back lobe when we do some chemistry. Okay, when we talk about backside attack, I'll be involving the back lobe a little bit. So here are the hybrid orbitals. What is each orbital doing? This is an orbital here, okay? It's an orbital. What is this orbital doing? It's interacting with the H orbital. What H orbital are we using? Yes. Okay. You got two orbitals here interacting, and there's two electrons sitting in there. And that's the covalent bond that's about that thick. Okay? Two electrons sitting in here in these orbitals. We can say these are still atomic orbitals. And this bond is made up of what two orbitals overlapping? This is a sp3 overlapping with an S. We've got four of them. What does an s orbital look like for the hydrogen? It's spherical. So I can draw maybe just spherical here, okay? And then I can kind of put two electrons here. Very simplistic, okay? Basically, I'm just trying to say there's two electrons. This is an H here. There's two electrons in here. These two orbitals are overlapping, okay? And it's making this covalent bond. So we got that 4 times. And you got 109.5 bond angles all the way around, and it's called tetrahedral. That's the geometry. For me, I only do electron geometry. I know in Gen Chem you do electron and molecular geometry, but for me, I don't discount electrons. Okay, it's organic chemistry. Only electron geometry. Of course, that's all it is, tetrahedral. What else do we want to say about this? There'll be more things to say as we see other examples. We'll move to SP2.
So, really this should be forming a new orbital, right? Since an orbital is only going to define where the electron is, right? Whenever you combine the S and the sp3. So I imagine it wouldn't look like a sphere combined with an sp3, like the actual orbital. How would it actually look?
Yeah, that's that deep question, book that thick. Yeah. You should,
Or are we saying that the electrons generally would be in that area right there? That will be where they're spending most of their time, is in that generic kind of overlap? Or?
What I'm saying is it's a very deep question. It's a little bit beyond this very simplistic what we're doing here. It's very good questions, but again, that's that book. Real deep. We just don't have the time and the focus for the course to go into that. If you take something like physical organic chemistry, you know, Chem 6983 or something, you'll get way into that. Let's move on to SP2. SP2, we're going to do ethene. This is going to be an example of SP2. Ethene, F is 2 carbons, ene is an alkene, and we have, to have an alkene, you have to have 2 carbons. So this is ethene, also known as ethylene. Ethylene can be polymerized to make polyethylene. Each carbon is sp2. So we go back and start off with ground state. I'll redraw this each time. We got the 2s and 2p. But this carbon is not in the ground state configuration. For example, there's no lone pair. Okay? Any bonding with the carbon is going to be in a hybridized, okay, a mixed state or a different state. We're going to hybridize. Now, sort of the leading thing you want to say is how many regions around this carbon here? Single bond region, double bond region, that's 3. Okay? With methane, how many did we have around the carbon? 4. 4 regions is tetrahedral, unless we say it's an exception, something different. 3 regions is what? sp2. Okay? So that's sort of a starting point. We want sp2. Well, what is sp2? That means what went into the blender? 1s, and how many p's? 2. So 1s and 2 p's, okay? This is going to blend. We're not going to blend this guy, just those. And if we put these 3 in, blend it up, what do we fish out? We fish out 3 equivalent hybrids, and what are we going to call these? 3 sp2 orbitals. Okay? It got blended up, and then we... but very importantly, don't forget this one. What did we not blend up? Yeah. One p orbital still there. We didn't blend up. Now we can put the valence electrons in, and they actually sit like this. Now you might say, well, shouldn't it pair up? Okay? And actually it's going to sit here. And now we can say, what type of bonds do we see here? I see 2 bonds to H, 2 bonds to carbon. We make a bond to an H, okay? Really, I should do this since we're going to go H and carbon. Bond to an H, okay? That's 1 electron from the H teamed up with 1 electron there, made bond. 1 electron from H teamed up with that electron, made bond. So there's your 2 bonds there. What other kind of bonding do you see that carbon making? They're the same. Let's look at this one. Now we have a double bond to carbon. The double bond is made here. The double bond consists of a sigma bond and the pi bond. I was trying to think of what we should have said about the methane. If you go back to the methane, and we had the, you already got it drawn on your paper. We had sort of this orbital here, and we made the 4 methane CH bonds. That's a sigma bond. Why is that a sigma bond? What's the definition of a sigma bond? Sigma bond is head-to-head overlap, okay? These are like head-to-head overlap. It's 4 sigma bonds. Hybrids make sigma bonds. Let's get to that by drawing the bonding here like we did with methane. Get rid of this here. So I have a carbon here. Your hybrids set your geometry. How many hybrids do we have? 3. There they are, okay? 3 sp2 hybrid orbitals. How are 3 orbitals spread out best? Trigonal planar. If I brought 3 balloons in here, tied them together, how would they spread out? Trigonal planar. Okay, that's nature. So, spread the 3 orbitals. What do these look like? I'm not going to draw them. But what do they look like compared to sp3? Shorter and fatter, right? Now when I draw them, they're going to look the same as before, because, okay, I can't be that precise. But we know if we were asked, they're going to be shorter. Okay, we got 3 orbitals spread out. If I drew a trigonal planar, I would draw it like what? Boom, boom, boom. That's trigonal planar, right? All on the plane of the board with bond angles of what? 120 all the way around. Boom, boom, all the way around. But really, this is orbitals. And there are the 3 hybrids. Why am I not drawing one forward, one back or anything? Because it's planar. It's all in the plane of the board. Okay? What is this orbital doing? Okay, there's 2 electrons there. What is this orbital doing? They can bond to H. What is this orbital doing? I need more room here, but we got the same identical carbon over here. And its geometry and every hybridization is the same exact thing, trigonal planar. So we put this orbital here. I don't know why I made it bigger than that one. You want me to make it smaller? What is that orbital doing? There are your 3 hybrids. This one's bonding to H. This one's bonding to H. But what is this hybrid doing? Here you have the 2 carbon hybrids interacting, making a bond. What type of bond do you call this? Sigma bond. It's head-to-head. 2 orbitals are head-to-head overlap. There's a sigma bond. And that's a what? Carbon sigma bond. Okay? Which one is that over here? That's right there. Made with the hybrids. Where the arrow is sort of, when I was dealing with this carbon, and then I'm showing the electron from that carbon as, instead of an electron, I'm showing it as a C. Okay? This is really the carbon on the right. What else is left on the carbon on the right other than the hybrids? P orbital. How is the p orbital drawn? P orbital is perpendicular to this plane. The p orbital is actually coming straight out at you. I can't draw it straight out at you, so I'm going to have to draw it up, and we're going to imagine that. Now I'm going to draw it sort of longer than the hybrid. It's a standard p orbital. Okay? P orbital. This carbon is the same exact carbon. It's just, okay? It's also got one. Alright? You see the hybrid? Now, the p orbital is only straight up if that system is here. If we turn these orbitals like this, but see, I can't do that. We've got orthogonal, we're perpendicular to each other. So these are your p orbitals, but what are these p orbitals doing? Now, it looks like they're not doing anything, but guess what they're doing? Side-to-side overlap. Now, the way I've got this drawn, it looks like, how can these orbitals interact? They're so far apart. But in real chemical life, they're close enough to have some interaction. But what type of, that's not head-to-head, what do we call that? That's side-to-side, not head-on, side-to-side. And what do we call a side-to-side bond? Pi bond. And so what do we have between the 2 carbons? A sigma bond from the hybrids, a pi bond from the p's, and together we have what? A double bond. Okay? The hybrids set your geometry though. Don't forget the p orbital left over that we didn't blend up. One thing we'll say moving forward a couple of times is because of the pi bond, these carbons can't rotate. In terms of sigma bond, these markers will do sigma bonds. Okay? Look at this. Boom, head-to-head overlap. There's a sigma bond. Head-to-head. Okay? That's the head, boom. Pi bond would be not head-to-head, but side-to-side. Okay? Now, sigma bond can rotate. Well, unless I break it. Now, these won't rotate. They did last time. Well, something should. The whole thing should. Okay, so it'll rotate and still be bonded. But if you do side to side, you cannot rotate the carbons because if you do this, that is no longer side to side bonding. Okay? We'll say this again moving forward. All right? That's a consequence of the pi bond. But
Was there anything else other than you can observe it not rotating that supports that it's a p orbital?
That supports what?
That isn't actually a p orbital that's left over after doing that? Just, that doesn't make any sense. And what would it look like if we took if we built it as being one piece at a time? From a carbon, added a hydrogen, and added another, or added a carbon, how the bonds actually form from there?
I'm not quite sure
I'll think about it.
what you're trying to get at. Let's now look at SP. SP, we're going to look at time. The YNE ending. Also, there may be things on the green sheet. B. What do we say about B? Pi bonds can't rotate. Okay? We'll see that more. Ethyne. C2H2SP hybridization. Ethyne is alkyne. You have to have two carbons to make an alkyne. It's actually also known as acetylene. Each carbon is sp. How do we know it's sp? How many regions are in this carbon? 2. Single bond region, triple bond region. 2 regions is sp. Thus, how many hybrids do we need? Regions come from hybrids. 2 regions, you're going to have 2 hybrids. All roads lead to sp. So we do our same thing we had before. Ground state, 2s, 2p. But these carbons are clearly not in ground state. There's no lone pair, et cetera, et cetera. This is actually exists in a hybridized state, so we're going to mix or hybridize. How does it actually exist? Well, SP involves putting what into the blender? 1 S and how many P's?
1 P.
We're just going to blend these. When we blend these, how many hybrids are we going to get out? 2 sp hybrid orbitals. Importantly though, what's left over? 2 p orbitals that did not go in the blender. They're still there. Okay, it turns out that the electrons are like this. Importantly, what type of bonds do you see here? Single bonds or sigma bonds? Sigma bond to H. What type of orbitals do you make sigma bonds with? Hybrids. So that hybrid, okay. Triple bond. Well, let's draw the carbon here. Okay. 2 hybrids. How are 2 hybrids going to be spread out? Linear. I brought 2 balloons in here and tied them together, they're spread out linear. If one of them was like this and the other one was like this, tell me about it, okay? We'll have a... No, if you tie them together, one's going to be like that, the other's going to be like this. The orbitals are like this. What do we know about the orbital shape compared to maybe sp2? Shorter. Okay? What is this orbital bonded to? 1s for the H, 2 electrons there, shown over there. What is this one bonded to? Actually, now the carbon, might be a little longer, but there is that. See, this other carbon is also linear. And so this bond angle here is what? 180. Okay? This guy's bonded to an H. Sigma bond to H, sigma bond to carbon. Sigma bond to H, sigma bond to carbon. What else is on this carbon? Not 1 p orbital, but 2. Well, 1 p orbital I can draw here. The other is the same exact thing. that's overlapping to make pi bond. That's actually all in the plane. These are straight to the side, these are actually straight up. What else is on the carbon? With your one p orbital, how about the other p orbital? The other p orbital is coming out at you, okay? And that's hard to draw. But basically the other two, and this carbon over here is the same exact thing. That one is straight up in the board, that one's coming straight out, this one's coming straight out, okay? But guess what? These two are also overlapping side to side, and gives you the second what? Second pi bond. For a total of 1 sigma and 2 pi's, and that's a triple bond. Now to try to draw in the other, I'm going to just sort of draw it a little bit like this. It's not going to work out. You really need to look at in your book and see some better 3D pictures. Okay. Should have been better thinking ahead a little bit. We may pull some of these up. Check out your textbook, and you can see they'll probably have them color coded. So what's between the carbons? Sigma and 2 pi. And that's shown right up here, right? Sigma, 2 pi, all together now, what is that? That's your triple bond between the carbons. Questions about hybridization? I did this with carbon, but guess what? Same exact stuff applies to nitrogen, oxygen, chlorine. Except for the others will be having long pairs. Before we look at some examples with heteroatoms, let's look at the table in here and sort of sum some things up here. These are the 3 examples I did. Each carbon within the molecule is the same. Both of these are sp2, both of these are sp. Bond angles. This is both HCH bond angle and also HCC bond angle. Okay, all 109.5. HCH or HCC, it's all 120. That's 180, that's for just linear. Length of bonds. Let's look at that. We should already be able to answer that though. This is length of the carbon-carbon bond. With the carbon-carbon bond, or bonding arrangement, that's actually a triple bond, but you might call this the interatomic distance. Okay. Which interatomic distance between carbons is longer? Well, obviously it's that one, the number. But why? Why is that longer? Well, what type of orbitals are used to make this carbon-carbon bond? sp3 orbital overlapping with sp3 orbital. We drew that. No, we actually didn't draw that with methane. With ethane. But that's the thinking you have to go. What type of orbital is being used? That carbon's sp3, right? I mean, it's not methane, but it's still 4 regions around it. It should be sp3. It should be tetrahedral. What orbitals are used to make this? And your sigma set your geometry and your bond length and your bond strength. What sigmas are used to make the sigma bond, or hybrids are making sigma bonds? sp2, sp2. And how about this? sp, sp. See right here. That's an sp, that's an sp, right? I mean, sp, right? Okay? So which bond's going to be longer? One that's made of sp-sp orbitals or one that's made of sp3-sp3? Well, this one, because sp3 orbitals are longer. Look above. Now, it's actually only order of about 1.5 angstrom. That exact number is not as important as the relative ranking. Okay? Now, what about bond strength? It's given in both kcal or kjoules. Let's just look at kcal. Now, the bonding between these two carbons is stronger than that, and that's stronger than that. Well, obviously, that's a triple bond. So it's stronger. Look at this. That one's 90. Single bond is 90. Why is a double bond not 180? You might say it's double. It should be double that. Why is it not 180? Exactly, because this is not 2 sigmas. All right? This is 1 sigma between the carbons. What's between the carbons here? 1 sigma, 1 pi.
So pi bonds are not as strong?
Pi bond's not as strong. Remember, I had to kind of tell you that even though they're far apart, there is some overlap. See, that side-to-side overlap is not as strong. But you say, well, the sigma's almost as strong as that because it's only 6 below 180, double. Well, there's something else going on. These sigma bonds are not equivalent, are they? No, because this sigma bond is made with 2 sp3 hybrids. That sigma bond is made with 2 sp2 hybrids. Which sigma bond is stronger? Well, here's your answer. A shorter orbital is going to make a stronger bond. Okay? It's almost intuitive, just like what's the stronger connection between me and him? That or something like this. Okay? Shorter is going to be stronger. That's actually a stronger sigma. So the sigma may be worth 120, but the pi is actually a lot weaker than it may look. Okay? Same thing in the strength and length of the CH bonds. In the end, guys, it all depends on what type of orbital is being used. The length of the CH doesn't vary much, but we see that the CH bond is longer here. Why is it longer? Because this is sp3 to s, where this is sp to s. The s is the same, but the sp is shorter. So that's a shorter bond than that. Okay, understanding your orbitals and really the length of them and how length correlates with strength, you can predict all this.
So how much is the bond angle exact whenever you start having 2 hydrogens versus 1 carbon on that, the hybrid bond? Is it still considered to be 1?
Your bond angles can vary a little bit from here, especially when you start getting long pairs. This is just kind of standard, and I don't do much beyond just saying that's standard. But bond angles can always vary a little bit. Okay, there's a question down below. There's Prozac. Rank bonds A to C in order from longest to shortest. Which bond's longer, A, B, or C? Longest to shortest, so A is greater or longer than B, and that's greater or longer than C. What orbitals are being used to make bond C? And again, just about any and all this, you're always looking at the hybrids. Pi bond doesn't set geometry, and it doesn't set bond length. Hybrids do all this. What are the hybrids that are used here? What's the hybridization of that carbon? sp2. What about that one? Also sp2. That bond is two hybrids overlapping to make sigma bond. And the sigma bond sets strength and length. Hybrids set strength and length. B is what? sp2, sp3. So one of the orbitals is a little bit longer. And then A is what? sp3, sp3. Okay? You got to know there's two H's there, and thus there's 4 regions around that carbon, thus it's sp3. There's one H there, and thus there's 4 regions around that carbon, thus it's sp3. And those are the types of hybrids that it has. There's questions like that throughout the handouts. Other hybridization examples. Let's look at carbocation. What is a carbocation? I'm not going to worry about bond angles here. That would be an example of a carbocation. Carbon that's a cation, carbon with a plus charge. You've got to be able to calculate charges. The carbon owns 3, because it's missing 1 plus charge. What's the hybridization of the carbon? And this is what I do. Most books don't do this. Graph the hybridization of that carbon. Just like we graphed the previous 3. Not the ground state, but the new hybrid state. Show it there. Did someone say the hybridization? sp2? Yes. Why sp2, Connor?
There's 3 groups. It's got 3 orbitals around it.
And we know that 3 balloons are going to be spread out in a
Trigonal
trigonal planar,
planar.
and trigonal planar is sp2. Okay? So graph that. When I say graph, it's basically very simplistic, okay? All we're going to do is say it's sp2. What does sp2 mean? How many hybrids? 3 hybrids. Very important, what's left over? P orbital. What type of bonds do you see here? And I'm taking you through the process, okay? What type of bonds do you see here? What type of bond is this? 3 sigma bonds to H. Single bonds or sigma bonds? Here we go. Sigma bond to H, sigma bond to H, sigma bond to H. Okay? 3 sigma bonds. That's what I see here. That's it. We're done. There you go. There's your graph. So-called graph. There is energy here, right? Is a p orbital higher energy than these hybrids? Yes. Because the hybrid has 33% S. It's got some S portion to it. With lower energy. What do we have here? That's an empty p orbital. Empty p orbital. Let me ask you a question. Would this molecule like to have electrons? Yes. It doesn't have a filled octet. It's got an empty p orbital. This could accept an electron pair. What's the definition of something that accepts an electron pair? A Lewis acid? Yeah, Lewis acid. Okay. How about a carbanion? A carbanion is a carbon that's an anion. By the way, is this geometry right? I can fix that by just drawing it like this, because we know the geometry around here is what? You know, it should be 120, right? Trigonoplanar. What if we take and have H's, and give this carbon a lone pair? What's the charge? Charge is minus. What's the hybridization of that carbon? How many regions around that carbon? Single bond region, single bond region, single bond region, lone pair region, that's 4. What's hybridization? sp3, how many hybrids does sp3 have? 4, because we put an S and 3 P's in the blender, we're going to get 4 out. Okay, what type of bonds do you see that carbon making? Sigma bond to H, sigma bond to H, sigma bond to H. What else do you see on that carbon? Lone pair. There it is right there, one of the hybrids. There's your lone pair. What's the true geometry of that carbon? One forward, one back. I'll do forward. Got H forward, H here, H here. What's going back here? Lone pair. I mean, that's an orbital. These are all orbitals, right? And then you got the, but see, that orbital is not interacting with anything. That orbital just contains the lone pair. Right? That orbital just contains the lone pair. Atoms with other than carbon. Okay, let's look at these. Let's look at the functional group page. What's the hybridization of that nitrogen right there? Lamisil. What's that commercial? They show the toes on fire? Lamisil? Bumble? What's the hybridization of the nitrogen? Well, we got to know that there's what there? Lone pair. How many regions around the nitrogen? 4. sp3. Until we do something different. If you graph that, what would it look like? It actually looks just like this. I'll try to do it here. You might, okay? We have 4 hybrids. What type of bonds do you see this nitrogen making? Sigma bond to carbon, sigma bond to carbon, sigma bond to carbon. What else do you see on this nitrogen? Lone pair. There you go. There's your lone pair. It's in a sp3. It's the same. It's isoelectronic to this guy. Except this guy was carbon. And when carbon has 1, 2, 3, 4, 5 valence electrons, it's a minus. But when nitrogen has 1, 2, 3, 4, 5 electrons, it's neutral. What's the hybridization of that oxygen right there, of the carbonyl? We got to know there's 2 lone pairs called standard bonding. sp2? Lauren? Andrew? sp2? Okay, so what does sp2 look like? How many hybrids? 3. And then a p orbital left over. sp2 because there's 2 lone pair regions and a double bond region. Okay, what type of bonds do you see that oxygen making? A double bond consists of what? 1 sigma, 1 pi. So make it. Sigma bond to what? Carbon. And what else to carbon? Pi bond. What orbital do we use to make pi bond? And all together, what is this? Should double bond. What else is on the oxygen? Two lone pairs. Where are they? They're in the hybrids. So if we drew this oxygen out, these three hybrids are, or what's the geometry of the hybrid? Not a trick. Trigonoplanar. So I'm going to draw one this way, and one this way. It's supposed to be trigonoplanar, like this. Okay? Then you got this carbon down here. Let's draw the carbon too. What's its hybridization? Also sp2. You see that carbon's down here, and it's also trigonoplanar. I'm going to draw one orbital up, one here and one here. But see, that's your sigma bond. That's a lone pair. Then what else is on this oxygen? P orbital. Now, if that's planar, the P orbital is coming out at you. Okay? But what else is also on the carbon? And it's coming out at you. And that's overlapping to make the pi bond that's there. It's hard for me to draw that, especially since I didn't really leave room to... see, they both have, I can't really do that, guys. There's also a pi bond in there. But what I like to do is graph, and ask you to graph it, okay? Between the C and the O, sigma bond, pi bond, two lone pairs, the hybrid set in your geometry. Let's do one more and then take a short break. So hybridization of this nitrogen here. There is a lone pair there. Aaron? Hybridization of nitrogen.
So the nitrogen should be sp. It's a triple one.
No, this one.
Oh, sorry. I did that one. So that one's sp2.
I didn't hear you.
It's sp2.
SP2. How do you know that?
It's got two sigma bonds, and then one lone pair. So.
I see. The sigma bond, what is this?
Oh, sorry.
You done? You done? You done?
Isn't it SP2 because the lone pairs participate in the conjugation?
Okay, somebody says SP2. Anybody else? Elena? How many regions around this nitrogen? 4. It looks like it might be sp3. If you came here from Gen Chem thinking it's sp3, that's okay. And nitrogen is actually sp2. Okay? This is an exception. sp2. And we'll say how to recognize exceptions in a minute. Since it's sp2, graph it. Graph sp2. What do we see? Okay, here we go. How many hybrids does sp2 have? I'm telling you it's sp2. How many hybrids? 3. What's left over? The orbital. What type of bonds do you see? There's no trick here. What type of bonds? Sigma bond to carbon, sigma bond to carbon, sigma bond to carbon. What orbitals do you want to use to make sigma bonds? Your hybrids, right there. There's your 3 sigma bonds. Okay, where must the lone pair be in this setup? Yes. LP and P orbital. There you go. There's your graph for that nitrogen. The question is, why would that lone pair want to be in a P orbital? A P orbital is higher energy than a hybrid. Yeah, but there's something else going on. If we graph that, so to get the nitrogen here, The important thing is next door, what's the hybridization of that carbon? It's also sp2. We'll look at this carbon. If this nitrogen's sp2, that means it's trigonal planar. That means it kind of looks trigonal planar. It's just a little bit turned from that, that's why this is kind of down. Or maybe that's not, okay, trigonal planar. So these are actually your orbitals, right? There's your three hybrids. This one's interacting with carbon over here. That one's interacting with carbon. Let's focus on this one. That one's also interacting with carbon. Here's that carbon. It's sp2. We're going to make one single bond and make the others trigonal planar. But what else is on this carbon down here? P orbital. It's sp2. Now this lone pair, if we put it in a hybrid, it would just be sitting there isolated. But if we put it in a p orbital and show a p orbital here, I put the lone pair there, I'm going to draw it like that. What can that p orbital do? Keep this in mind, guys. Orbital overlap, which is bonding. It's a good thing. Is there potential for orbital overlap in this scenario that I'm showing you? Yes. And what you actually have here is two orbitals overlapping, and how many electrons in the system? Two. They're coming from the lone pair. The reason this adopts sp2 is because the lone pair overlapping with the adjacent p orbital is actually more stable than if we did it sp3. So when does this happen? Whenever a lone pair is next door to what? A p orbital. Whenever a lone pair is next to a p orbital, that lone pair is typically going to want to be in a p orbital itself so it can interact with the adjacent p orbital. And what do we call that, Udong?
Conjugation.
Conjugation. Is it Udong or Utong?
Utong.
T?
Yes.
That's called conjugation. What is conjugation? Conjugation is p orbital overlap. What if I made this sp3 and made all these hybrids? Would we then have p orbital overlap? No, there wouldn't even be a p orbital here. Making it sp2, the exception, allows p orbital overlap. Okay? This is the foundation of resonance and conjugation of lone pairs being conjugated. Anytime a lone pair is conjugated, it's got to be in a p orbital because conjugation is p orbitals. Question?
But it doesn't make a double bond there?
There is some double bond character there. Yeah. There is double bond character between this nitrogen here. That gets into a limitation of Lewis structures. And that gets into resonance hybrids. Whenever we draw Lewis structures, they're very static and almost fake, especially when you have conjugation going on. And you have to just know as a good organic chemistry student that there's some p orbital overlap here. It's not shown by that simple structure. Tom?
So you said the exception is whenever a lone pair is next to the orbital. What do you mean by next to it? How do
The neighboring atom,
okay.
for us, in some advanced cases, it may be one over here. Boom, boom, boom. Maybe there's a p orbital there, and if this one, if it can overlap, but for us, it's adjacent atom. Let's see. Is that written anywhere? Probably is, because I get handouts that things are written there for you to read. What does it say right here? There you go. While we take a 4-minute break, read that right there. Also do this. do the hybridization of the nitrogen right here, that nitrogen guy, and this nitrogen guy over here. Okay, that one and that one. Any others you want to do? And on the drug sheet in the workbook, it asks you to do them all. Okay? Take a quick 4-minute break. Want to stretch, go to the restroom, we'll get going. I may or may not stop this. Yeah.
So, clear to me before we I was curious as to how carbon wise it's going to
The whole
along.
column here.
Trying to get that. Because there's
How are you?
So this one?
Well, the theory you want is just so deep, you know. Well, see, the way you do it is you gotta learn it. I will be facing this one.
I think she's right about this one.
Really good class.
It's gonna happen.
Nature that he's stopping the pond.
This is
And you probably do math involved also.
just. But this.
Get into deep.
I should be able to get
It's okay, I mean, a lot of things to do.
And the mod is literally the hand next to the one. All of
No
mine.
matter what about it, student still has the.
And there's a.
That's what mine is. Like, that's what
Is that all you?
These y'all, the ones sticking up are the tours. They're interactive.
They're kind of actually good up along, but it's
Yeah, all these bonds are gonna be like in line with it, like, the other one's like this, and so because only the hybrid ones are bonds. Are part of the single bond. Even that hybrid are. But yours, I don't hear why it'll be, it'll end up strengthening the bond.
so it's kind of like a 1.5.
Yeah, the hybrid, Next to the base. There's no bond that is consistent. So that's two.
Three bonds on it. It's not gonna have that title.
A bond number is-
You want it each chart, oh, I see.
Have a height.
I know.
Just the one. Not the- Well, it's over. Because that, if you draw it out, it's good in yeah, choose the model.
For the, it's the same as that one.
Okay, guys, want to collect your pre-course questionnaire. Please pass that to the side.
To the side or
To the middle. Number what there? Which compound? Bottom left? Yeah. Only one more. We should do that one too. Okay, guys, everybody back? Sounds like it. Let's see. How about this nitrogen here? Hybridization? Nitrogen's sp2. Why when it has 4 regions around it? Looks like it should be sp3. But see, what's next door? Over here you have a p orbital. You see there's a p orbital there, there's a p orbital there. That's that pi bond we see there. Okay? This lone pair is going to want to be in a p orbital too. I don't know why I drew that bigger. Why? Because it can interact with that pi system up there. Anytime a p orbital is, anytime a lone pair is next to a p orbital, the lone pair is going to want to exist in the p orbital, so it can do this because p orbital overlap is a good thing. It's called conjugation. Thus, knowing that it's sp2, we would graph it as just like the other nitrogen we did. 3 hybrids. The hybrid making bonded carbon, and bonded what? Bonded H, and the lone pair would be sitting up in that p orbital. Okay, that's the exception, just like we did before. The other nitrogen over on the right, what's its hybridization? You got to know that this is a nitrile. It's condensed down. The triple bond between is not shown. So how many regions around that nitrogen? Lone pair region, triple bond region, 2 regions, so it's sp. And if we graph sp, how many hybrids does sp have? 2. What's left over? 2 p's. What type of bonds do you see this nitrogen making? A triple bond, which is 1 sigma and 2 pi's. So this is your triple. Where's the lone pair sitting? Sitting in the hybrid. Hybrid set in your geometry. You have two hybrids, back lobe over here, back lobe over here. That's not a p orbital. Okay? That's two hybrids with back lobe not shown. One side you have a lone pair, other side you have one electron interacting over here. I won't do that, but okay. One orbital has lone pair, another is making a bond, carbon, and then you have p orbitals here making two other pi bonds. Because that carbon over there also has two p orbitals, because it's also sp.
So if there was a double bond next to that one,
This exception, it requires some more discussion. The exception only takes place when it looks like sp3, but it's actually sp2. You're never going to see it, maybe very rarely, unique cases. If it looks like it's sp2, it's never going to become sp. Perhaps, but mainly when it looks like this, sp3, it's actually sp2. Problem is, you can't just go putting everything in p orbitals, because if there's one next door, there's only one. And so it's only going to be one overlap. You can't then put two over here, because two can't overlap with one. Keep asking. Question?
For that functional group, would you prefer nitrile or cyano? Or does it matter?
Really either works. Cyano is like the group itself. The whole compound is called a nitrile.
Okay,
It's sort of like an alcohol is the whole compound, but the actual group is called a hydroxy group.
okay, so does it matter which if we call it alcohol or hydroxyl?
For me either.
Okay, but then with carbonyls, if you ketone about
Well, carbonyl is not an actual functional group.
that. Okay. that's-
Carbonyl is just a component of many functional groups.
Okay,
So no functional group is called a carbonyl, strictly speaking.
okay.
How about this oxygen here? What's the hybridization? What is this, an ether? It's an ether. What's the hybridization? Two lone pairs.
SP3.
that's your double bond.
I see double bond, I see p orbitals next door.
Two orbitals on both sides.
It's going to be sp2. Okay? I'm not going to get into that. We need to move on. Think about why it's sp2. It's the exception. Only one lone pair is going to move into a p orbital. And that lone pair is actually going to overlap with both adjacent p orbitals. Question? A word about molecular orbital theory. Okay. What we're doing basically is valence bonding, it's called. Okay? We are keeping atomic orbitals, and we're just showing the atomic orbitals overlapping like head-to-head or side-to-side. Another bonding theory is molecular orbital theory. It's more advanced. In some cases, it's more correct, but it's way more advanced. One place it does come up is if you draw a Lewis structure of oxygen. You'd say this looks good here. Okay, oxygen has two bonds, two lone pairs. Two bonds, two lone pairs, both oxygens have octets. Good structure, right? Okay. The problem is, this structure does not fit experimental evidence. We know from experiment that oxygen is a diradical. That means it has two unpaired electrons. Well, where are the unpaired electrons? I mean, that's a lone pair, pair, bonding pair, bonding pair. Okay? So it's like on Family Feud. We're wrong here. Something is wrong. If you do a molecular orbital description of oxygen, you see that it's a diradical. Okay? So, there is a difference between valence bonding and molecular orbital theory. I don't do any molecular orbital theory in organic 1 much at all. When we get to organic 2 and we do aromatics, we will look at molecular orbital theory a little bit more. Okay, just enough to do aromatics. Okay, polarity of covalent bonds. We need to move to the next handout, physical properties. Now that we know some basic structure, we can start predicting properties. Here's some warm-ups here. We'll look at things like polarity. Which compounds below are nonpolar? What type of intermolecular forces would you predict for vitamin A? Okay, on down the line. We'll also do acid-base chemistry. Lots of things to be looking at there. More of a drug application over here on physical properties. And we'll begin with polarity of covalent bonds. H2 would be a nonpolar covalent bond. Okay? The H's sort of equally share the two electrons. The two electrons sit equally between the H's in that covalent bond. On the other hand, HCl, chlorine is a little greedy guy, okay? Loves electrons. So the two electrons here pull towards the chlorine, and you're going to get something that looks more like, this. The electrons there. Now, when we draw the old dash, that's very simplistic. But in real life, they're pushed towards the chlorine. And we can say, well, chlorine sort of has more of the electron density. And then we can say, well, chlorine is going to have some partial minus charge because of that. All right? And just in terms of just charge fit. And because the H doesn't have as much electron density, it's partial plus. So it can be shown like this. We also have dipole arrow indicating the electrons are moving towards the chlorine, leaving this end positive. Now that's a partial charge, not a formal +1. Now, of course, this could become a +1 if this ionized, and the chlorine, instead of just pulling, if it said, okay, I'm just taking, if it just took them, that would become an H with no electrons, and that's plus, and the chlorine would, of course, what does this arrow mean? Covalent, the two electrons are moving on to chlorine as the fourth lone pair. That's now chloride minus. So it could ionize, and then it would be two formal charges. And if you put it in a polar solvent, it would typically ionize. Okay, we have polarity other places. Carbonyls are polar. Double bond is polar because the oxygen is more electronegative. And so the carbon of a carbonyl is partial plus, the oxygen partial minus. Pi bonds are particularly polarizable. It means a pi bond is easier to pull than a sigma bond. Because pi bonds are Hilda's type. So that greedy oxygen can pull it more.
In the SI yesterday, we did carbon monoxide. Is there a way you could do that one real quick? Because it seemed like it was strong to the electronegativity.
Carbon had a minus.
Right, and the oxygen had a plus.
Really, I'm not going to do it here. We can do it another time. Stop by. But yeah, the carbon monoxide, carbon is actually minus. But a reason it's minus when carbon doesn't like to be minus is because the oxygen is pulling. And so the carbon's like, I don't mind being minus because I got this pulling. So it kind of all works out. Okay, we have other polarities. Basically, what do you need to know to predict polarity? Electronegativity. So you have to have your periodic table. Something like the ICL. Which halogen is partial plus? The iodine, because the chlorine is more electronegative. Okay, higher in the periodic table. All right. Water. We have dipoles coming in, so the oxygen is partial minus, leaving the H is partial plus. A lot of times we don't draw things with correct geometry. That's actually tetrahedral with the 109.5 bond angles. Have something like this, methyl bromide, bromine pulling, leaving this carbon partial plus. Okay, as you said here. predicting partial minuses and partial pluses helps you then predict many other properties and reactivity of molecules. Because, as we learned in first grade or somewhere along the line, minus is like pluses. And so if this carbon has some plus, and you put a minus nearby, it'll be attracted to that carbon and you could maybe get some reaction. Okay? So from individual dipoles, we can calculate or determine net polarity. And so net polarity would be saying, is water polar or not? So we got to know structure. Okay. This is oxygen with H, 2 in the plane, 1 forward, and 1 back. Those are the other orbitals. Those are lone pairs. Okay, so this is really 109.5. We have individual dipoles that look like this. And the question we ask is, for the net answer is, do those dipoles cancel each other out or not? And this would be vector summation. To cancel it out, it has to be equal and opposite. Are those equal and opposite? No. Those actually reinforce, and you get a single net dipole sort of straight up through here. It kind of looks like that, with this being the positive end and that being the negative end. Of course, that's the negative end because those are electrons up there. That dipole, also known as dipole moment. But it has some direction. What do you call it? Kind of a vector direction. What is a polar molecule? CO2, polar or not? Well, you need to know Lewis structure, right? CO2, put together a Lewis structure, you will get this right here. Carbon making 4 bonds, each oxygen 2 bonds, 2 lone pairs. Is the geometry right? What's the geometry of this carbon? It's SP. Okay. Graphing this, doing your orbitals, that'd be a good exercise to do. Okay. But it is SP. So it is linear, so we got the geometry right, you know? So this is the thinking we need to do. So what type of dipole do we have here? Oxygen is a greedy. So is that one? Are those equal and opposite?
Yes.
Yes, they are in this case. So is, what's the answer for CO2? Non-polar. Okay. What about SO2? We need to know. We need to show a Lewis structure so we can predict geometry and then show our dipoles. Let's see. How many valence electrons are we dealing with? 18 valence electrons. Usually sulfur's in the middle of things like this, yeah? Sulfur, oxygen, oxygen. Let's see, I don't have any H's. I'm going to put my lone pairs here. How many lone pairs do I have? 18, 2, 4, 6, 8, 10, 12, 14, 16. Now put one here. 18. Are we done? Can we do a better structure? Does this sulfur have an octet? 2, 4, 6? No. What do you want to do? Well, let's ask these to move in here. These electrons move in to make actually pi bond, and that's going to give two lone pairs. Lone pair here, don't forget about that one. 18 valence electrons. Now sulfur has an octet, 2, 4, 6, 8. So does oxygen, 2, 4, 6, 8. So does oxygen, 2, 4, 6, 8. But we have charge, because that's not a typical oxygen. What's the charge of that? That's minus. That's a typical oxygen, 2 bonds, 2 lone pairs. That's basically oxygen, that's not typical, what's the charge of that? Charge of that sulfur, Taylor? It owns 2, one of those 3, one of those 4, one of those 5. It owns 5, but it's supposed to own
6,
6, so it's missing one.
right. So a negative?
No, if you're missing an
Oh, the missing
electron,
one, a positive.
missing an electron, you're positive. See, this cancels. See, SO2 is neutral. If that was charged, I should have shown a charge. It's neutral. See, it's net neutral. There you go. That's a better structure. These are resonance structures. Okay, that's a better one. Now we can say geometry. What geometry do you expect for that sulfur, for hybridization? How many regions around it? 1, 2, 3. What do you want to say? SP2. So I'm going to draw it, SP2, trigonal planar, with a lone pair here, oxygen here, double bond here. Okay? So now we have dipole, S and O, yeah? Oxygen's more electronegative. It's pulling even though it's minus. There's another lone pair there. Are those equal and opposite? No. Polar. What's the big difference between SO2 and CO2? The big difference is because sulfur has a lone pair, it makes it trigonal planar. And then these don't cancel out. There's a charge here.
So why don't we?
You see over here, carbon didn't have a lone pair, and so it was sp linear. Question?
Why wouldn't this one do the lower or expand its octet to lower its formal charge for the sulfur?
You want to put what lone pair in the p orbital?
So put 2 double bonds, or am I missing something? Take an extra one of the lone pairs from the other oxygen and move it to a double bond on the top one?
Double bond here?
Yes.
Well, you could. I mean, if you want to show that structure, make that a double bond.
Well, won't that change the actual physical structure of the, because then you don't have that. No, I guess it wouldn't change. I'm just curious
You
as to
still
what
have
point
a-
it would be.
You
Because
still
now you
have a lone pair on sulfur, wouldn't you?
But now you have, now you've reduced.
No, you're actually onto something here. I'm kind of lying to you, I'm leaving something out. That sulfur is actually not sp2. Because that sulfur has d orbitals. Okay? See, sulfur is row 3, has d orbitals. And I'm not counting those. So you're exactly right. Yeah, it has d orbitals. And that's how you're able to do this. Because see, at this point, you have 2, 4, 6, 8, 10 electrons around sulfur. How do you do that? Because it has d orbitals. All right. So you're very right about that. We have to get into d orbital hybridization. We're not doing that. The main thing is it's not, if you approach it this way, it's not sp. Since it's not sp, the 2 dipoles don't cancel out. Okay? It's got some d orbitals. Sulfur put d orbitals into the blender as well.
So, for the carbon dioxide, since it's non-polar on average, but it has actual, like it's kind of unstable, it's pulling to either side, will that give it like greater temporary dipoles than say if it was something that was typically less or weaker bonds between the C versus, instead of O's, something else? Maybe like CIs, or not CI, C, whatever that TE is.
Yeah, there is some temporary dipole. There's a lot of partial plus here, but there's also partial minus down here, and it all kind of cancels out. The carbon does have a lot of partial plus. But you got to remember what you can actually measure. Pretty sure you can only measure a net dipole. You can't measure individual dipoles. So what we're really looking at here is the net dipole moment. And the net dipole moment for carbon dioxide is, it's not polar. Cyclone gave us a polar model. Because behavior is something that we observe and it's, you know. Okay, carbon tetrachloride, polar, non-polar? Okay. It basically is carbon bonded to 4 chlorines. What's the geometry or hybridization for the carbon? sp3. So we have bond to chlorine, 2 in the plane, 1 forward, and 1 back. This is standard tetrahedral. Every one, we got 4 polar bonds. Are these equal and opposite?
Yes.
This is where I should have brought my models, and I apologize for not doing that today. But if you look at a tetrahedral, basically the 4 things are spread out very equally. And those are equal and opposite dipoles. Really, if I had a tetrahedral, if one was sticking straight up, the other 3 would be down, but in sort of a tripod manner. And the one sticking up would be canceled by the 3 that are down, but are going boom, boom, boom. So they each kind of count a third because they're not going straight down, they're going to, okay? We can see this better with a model, and I'll bring models tomorrow. But in the end, when you have 4 identical things on a carbon like this, all dipoles cancel. Now, of course, if one of these was a bromine, well then not, because you got a bigger dipole this way than the other way. Okay? So this is non-polar. Now, of course, if one of these was an H, I know you can't erase as easily as I did, but just beside the chlorine, put an H. Okay? But if this is an H, what do you think is the net result?
As a hydrogen.
Well, the one thing we're going to do is make a statement here. There's a slight difference in electronegativity between C and the H, but it's so slight that it's considered no dipole. Okay? No dipole here. That's typically the answer. So what we have here is 3 dipoles going that way, nothing here. And what's the net result? Polar. CH2Cl2 is called dichloromethane. Dichloromethane, if you did not know structure, you might say, hey, chlorines are equal and opposite. It's not polar. But what's the problem with my structure? It's really tetrahedral. It's not planar, what do you call that? Cross tetrahedral. So if we draw that, put chlorine up and like this, and it doesn't matter where you put the chlorines, it's going to get the same answer. H, H, you see you have a net dipole through here, and this area is the negative, and this area is more positive. So you have to know true geometry. Now, what's the extreme of polar covalent? I kind of showed this earlier with the HCl ionizing. But the extreme would be ionic. I mean, something like sodium chloride, it's not covalent ever. Okay? It never was. There's such a large difference in the electronegativity that when this is formed, the electrons just all sit on the chlorine. They all sit on the chlorine and the sodium sits at the plus, and so you have two ions called an ion pair. It never was this, but I kind of showed it. See, here you have such a difference in electronegativity that we can envision maybe the chlorine just saying, I'm no longer sharing with you, sodium. I'm just taking them. Okay? Enough of this. And it just took them.
So what does the orbital structure look like on chlorine then? Is it going to be the S and 3Ps, or is it going to be still hybrid?
I'd probably say that's sp3.
SP3 hybridization?
You know, four long pairs around in a tetrahedral ring.
Oh,
We've got four lone pairs around and expect four lone pairs to be spread out tetrahedral.
okay. What about neon or a noble gas or A?
Well, first off, hybridization can often be different than the standard predictor. So in a lot of cases, you have to really study it. You know, we're kind of doing just the standard. There's many exceptions to plain hybridization. For example, phosphorus. Phosphorus tends to not do standard hybridization like nitrogen. How do we know that? From experimental evidence. So you have to adjust, and you have to say, why is Mother Nature like that? Okay, we're kind of learning the standards. Lots of exceptions. Okay, so that's polarity, predicting polar, nonpolar, and sort of visualizing the dipole direction. Physical properties. Guess what they're based on? Polarity, structure. Okay, everything we're doing is setting a little bit of foundation to move on to do the next thing. Main things we'll look at are boiling point, melting point, and solubility. Solubility being hugely important. If we do anything, usually dissolving something, either in your iced tea or in your IV bag or in a nuclear reaction at the plant. Okay, boiling point. Well, to vaporize or boil a compound, you must overcome all intermolecular attraction. Okay? If you're 44 different molecules, okay, if you're out there sitting with each other, you're probably going to be interacting with each other. Unless you're just non-polar and you're just very bored. Okay? But probably you're going to have a polar in, so you got some plus. What about your plus? And you probably got a minus in, and so you're going to be a little bit attracted to his plus. Okay? All right? And then, because you got a polar, then you obviously got some dipole, but you wouldn't have a plus unless you're an ion. And so you're all the same molecules, so you're all going to be linked up with some dipole interaction. That's why we predict dipoles, because if we have a polar molecule, the adjacent polar molecule will have a minus in and a plus in, and they can come together and attract to each other. Well, that is called intermolecular attraction. Two different molecules. But to get a compound to boil, we have to overcome that, because the attraction between you two guys has to be totally broken, and then you kind of float free and you become a gas. Okay? Not much intermolecular attraction in the gaseous state. In general, higher intermolecular attraction equals higher boiling point. So if y'all are holding one hand versus holding three hands, there's going to be a difference. If all you guys are holding three hands, I'm going to have to put more heat into you to get you to boil. What are the types of intermolecular attractions? Also called IMFs, or intermolecular forces. Also called non-covalent interactions. Because we're not talking about you making covalent bonds, we're talking about you just having electrostatic attraction. Either from being an ion or partial positive. Non-covalent interactions. Here are the four types. Van der Waals attractions, also sometimes called London or dispersion forces. Okay? For me, it's basically all the same. These are also in order of ranking, which is weaker to stronger. Dipole, dipole, and that's kind of what I described here. Your negative end attracting to her positive end. Hydrogen bonding. This is actually nothing more than just a very strong dipole-dipole, just a special case. Strongest is going to be ionic. That's where you actually have a positive charge because you're an ion, and then she has a negative charge because she's an ion. That's the strongest. Formal charges. That's formal charges. That's the strongest. Let's look at each of these. They're numbered on the left. Number 1, van der Waals. How this affects boiling point. Look at these 3 examples. This is just hydrocarbons. Plain saturated hydrocarbon. That's called propane. We'll do nomenclature a bit later. 1, 2, 3, 4, 5. That's pentane. Pentane has a higher boiling point. Okay? See, room temperature, this is actually a gas because it's boiling at room temperature. But at room temperature of 20 degrees, this is not boiling, so it's a liquid. Why does this have a higher boiling point? Well, the simple answer is it has more intermolecular attraction. Because that's why things have higher boiling points. But why does it have more intermolecular attraction? Because it has more surface area. This is just van der Waals. What's on the surface of molecules? It's not buried in the nucleus. What's on the surface? Electrons. Okay? Electrons on the surface. Now, why would electrons want to be attracted to electrons? Not really. But electron clouds can be kind of disturbed. And as one molecule approaches another, this is sort of hand waving to me. My electron cloud can bump into yours, and it can make your electrons move a little bit. And apparently, a little bit of positive develops on this side of you, because I pushed you a little bit. It's very weak, very fleeting, and a little bit nebulous in my mind. Okay, but it's called van der Waals or London forces. So as you bump into each other, you create these fleeting charges on the surface. Very weak. The main thing here is the more surface area you have, the more of these partial positive, very weak charges develop, and the more attraction. So it's mainly surface area. Which has more surface area? The bigger one. Okay? That's why the boiling point's higher. I mean, do you have any dipole here? You can't really describe dipole. There's no dipole between CC and there's no dipole between CH. Not a polar molecule. Fleeting temporary van der Waals attractions. Well, why when we go over to this guy is it now lower than that one? I mean, that's 5 carbons. That's also 5. Why is this one lower? What's our explanation? Not as much surface area. Because the surface area is not as much, you can understand that because that center carbon is sort of buried in the middle and it doesn't contribute to the surface area. What can we thus say about branching? Branching diminishes surface area. Thus branching diminishes boiling point. Okay? Bring it right over here. Branching lowers boiling point. Read that and make sure. Okay, I'm not going to read it to you. Okay, let's look at number 2, which was what? Dipoles? Look at the difference in these boiling points. Pentane at 36. If we slip a carbonyl in there, it goes up to 76. And then with a chlorine there, it's 78. Why is this one higher than this one? What's your argument? Well, here we have a permanent dipole, right? Now, would you expect this compound to be polar? I only see one dipole. It's not, there's nothing canceling it out. That's a polar molecule. Okay. That means it has a partial plus and a partial minus in every molecule. We're back to this. Your partial plus in and your partial minus, what are y'all going to do? Y'all going to attract together and it's going to keep y'all intermolecular attraction. Okay? Now, does this have any permanent dipole? No. It's like y'all sitting next to each other, ignoring each other. Unless y'all happen to bump into each other and get this fleeting van der Waals, which is very weak, and it's like, what's that? Okay? Fleeting, okay? It's that weak stuff. We're doing dipole-dipole now, permanent. This is stronger. More intermolecular attraction, higher boiling point. What about the chlorine? Why when we sip a chlorine on the end does the boiling point go up? Oh, now we have a permanent dipole. It's a polar molecule. Dipole-dipole interaction. Now the partial carbon interacts with the negative chlorine of two different molecules because we're doing intermolecular attraction. Different molecules. Okay? I illustrate this down here. Okay? The negative end, this little here is just sort of an association. It's not a covalent bond. It's a non-covalent interaction. It's showing the minus and the positive sort of attracting to each other. Now all the molecules are kind of holding hands a little bit. Not vice grip, but good holding hand. What's the next one? Number 3. Hydrogen bonding. This alcohol has a substantially higher boiling point than the chlorides. Why? Well, we're under number 3, so the answer is hydrogen bonding. What do we have here? I have a permanent dipole. I also have this OH, and there's a permanent dipole. Like they're both permanent dipoles.
Is that always going in one direction?
You also have a dipole, another dipole. Nobody's ever pointed that out before. That actually can give you the answer, but it's not. The main answer here is the dipole, whenever you have an H, and whenever the other atom is an oxygen, nitrogen, or fluorine, that's listed here, okay? That dipole is particularly strong. And when you have something that has that dipole, the intermolecular attraction is called hydrogen bonding. It's just another dipole-dipole interaction, but it's particularly strong when the H is on an O, N, or F. So that right there is a particularly strong question.
Yeah, on the OH, shouldn't it be going the other way? The arrow is going towards oxygen.
Yes, thank you. I really don't have a bond out there, but yeah, it should be going the other way. Again, it's basically just another example of dipole-dipole, but when you have an H on one of those atoms. Now really it's only these two, because the only way an H can be on F is if it's HF. So it's never going to be part of a molecule. Really O or N. Particularly strong. And we can show an interaction here, just like we showed before. But here, because it involves this H that's on O or N, we call it hydrogen bonding. And so we can call it maybe something like hydrogen bonding network. Okay? Where you got the positive H interacting non-covalently with the negative O. And all these molecules are like they're holding hands, but what's stronger than the previous example. So now it's more like a vice grip, because it's a strong polarity. Okay? There's a couple of questions to answer. We'll pick up here, particularly over here. Answer questions through here. Let me make sure I reiterate this. As we move forward, please always look ahead the next couple of pages, and if there's questions asked, please try to answer them, so that when you come to class, you'll be ready to get your questions answered. And there's the questions you had with the questions. We'll also be moving on to acid-base chemistry soon. Okay? You check the daily outline, please start looking at acid-base chemistry. See some of you this afternoon and, after lab check-in for the IR lecture. I'll see you. I'll come by the lab upstairs.
I work at a famous company. It's a